It's a perfect moment to start. Wonderful. Good to see you all. Thanks for coming. It's great to see you, even in this, not only in this awkward time, of course, but also in the holiday season. That we got quite a crowd together of quantum error correction enthusiasts. So thanks for coming. In particular, thanks to Mike Vasmer for coming, at least virtually in these days. That's all we can offer at the moment. So Mike is kind of part of the family. He did his PhD at UCL with somebody else who's part of the family, then Brown, who I even worked with in my old days when I was a postdoc at Imperial, and he was a PhD student at the time. So we did lots of stuff together. It's also nice to see that Mike is moving on here. And Mike has been doing spectacular work on quantum error correction in the past, and would now like to talk about a specifically intriguing topic that came out that we were excited about, and then we were so lazy, so we thought that we would invite him and hear the gospel from the saints, so to say. So here we are. So Mike will talk about single-shot quantum error correction with the three-dimensional subsystem toric code. Thanks for coming, and the stage is all yours.
Thank you very much, Jens, for that lovely introduction. So I'm just going to share my screen here. I'm very, very happy to present this work at this meeting. This project took me and Alex, and you can see also quite a few years to do. So we're very happy to have it out, and we're very excited that there's some interest in the community. And so just to explain these slides, I'm going to actually use Alex's slides from TQC last week, but the idea is I'll go through them quite slowly, and please interrupt me with questions, because you can all watch Alex's TQC talk on YouTube if you want, but I think the idea here is I can swap back to the paper. I can explain any details or anything that you want. So please, questions are very much encouraged. Okay, yeah. So let's just check it's working. Okay, you can see them moving, right?
That's a common flaw and mistake. I know this problem. For reasons completely unknown to me, why you can't go away from the first slide. This does happen. And there's been more than one talk in the past, but not this one. It does work. Okay,
good. Okay, yeah. So the question the big question as we're all kind of working on, I suppose, is how to build a scalable quantum computer. And a lot of us also want to look at topological codes, because they're something that we can imagine we can engineer actually in the lab. And these are things that, although maybe haven't quite been realized yet, are definitely people are making big strides towards this. And the archetype of a topological code is QMIO's 2D toric code, which I'm sure everyone is familiar with. And this is very nice. It has this planar architecture with geometrically local parity checks, and also a high threshold in practice. And the question is okay, but what about if there in the quantum case, unlike the classical, we have to worry more about measurement errors? There's a standard method for kind of fixing this problem, and that is to repeat the parity check measurements. But the problem is this introduces some kind of overhead, so you have to repeat the measurements.
Sorry, there is a bit of noise in the background. Is that on your side or somebody else's side? Or maybe if it's on somebody else's side, it's better when we mute ourselves, unless we have a question. That's maybe easier.
I don't think it's on my side, but I could also hear it.
Okay, then let's maybe mute ourselves, and sorry for the interruption.
Oh, yeah, okay, so we have to repeat the parity check measurements, and this incurs some kind of overhead. So you see you have to do it order kind of L times, if you're looking at L by L toric code. And this is something we'd like to avoid, because it's slowing down the clock speed of our computer. And so there are results that say we can avoid repeating these parity measurements, and there's various kind of results looking at this. However, when we do this in general, you could do this with the 2D toric code. You could find a generating set of the stabilizer, which would be single shot in that you wouldn't have to repeat the parity check measurements. But the problem is you'd lose the geometric locality, and ideally we want to keep this. So instead, what we want is something that can we can measure the syndrome even that when we have measurement errors in a robust way, but keeping the parity checks local, geometrically local. And this is something that's been achieved in the past in a seminal work by Hector Bombin, where he looked at single shot quantum error correction with the gauge color code. And this is a big inspiration for our work. And in some ways you can think of what we've done is introduce a kind of model for similar to the gauge color code, but kind of based on the 3D toric code instead of the 3D color code. There's also this interesting question about the connection between single shot error correction in 3 dimensions and self corrections in 4D. Obviously, we all want to know if it's possible to build a self-correcting quantum memory in 3D. And it seems that this self-correction implies a single shot error correction, but the converse is, I would say, probably not true. Although, there's still questions about because the gauge color code, for example, is it's a subsystem code. So if you look at the Hamiltonian, it's it's not commuting. There's kind of questions about is this actually a quantum memory or not? I tend to be on the side of no, but that this connection is interesting, and it's another hope of this looking at this subsystem toric code is to maybe make some more progress on understanding this connection and self-correction in 3D. So maybe I have time to comment on that a bit later.
That's super interesting, but like for now, either direction of this implication is not fully settled, right? Of the connection between single shot quantum error correction and being a self-correcting quantum memory, or not?
Yeah, I wouldn't say it's like proved in general. I think like at least the 4D toric code is, I would say, is a single shot code, because it's like the loop sector of the 3D toric code. The errors, you can view the errors for one of the error types as having syndromes, which are these closed loops, and then if they're broken by you have wrong measurement outcomes, you can join them together, and then this would be like a single shot procedure. And I've looked at this before with work with Yoshka and Earl and Armanda, and so in the 4D toric code, both the errors would have this structure, so I think it would be a single shot code. But yeah, in general, I think the connection is unclear exactly how these things relate to each other.
Okay, wonderful, thanks.
Okay, so here's like an outline of what we're gonna talk about. So so what we're gonna look at is this 3D subsystem toric code. I'm gonna give you the definition, and then we're gonna talk about the properties, about how to do single shot error correction with it, and also talk about a universal gate set. So the nice thing about this 3D subsystem toric code is it's much simpler than the gauge color code. I would say, like, in the color code, you have this thing where you have the different charges, and then the different color charges can, like in the 3D case, 4 of them can fuse, for example, and it's a lot more complicated, especially with the gauge flux as well. But this, as you'll see, the 3D subsystem toric code is a lot simpler to understand. So we find that we can actually do the error correction both with the noisy measurements and including noisy measurements. We just need to use minimum perfect matching, which is quite nice. So in the gauge color code, for example, previous numerics used RG based approaches, which generally have worse performance. But the nice thing here is you can just use matching for both steps. And then I'm going to discuss a bit talking about how do we prove that this thing has single shot error correction. And in this is a really I'd say mainly something that Alex did, but what we were looking at really is this proof that Hector did in one of his papers about proving single shot error correction. And we took this and we adapted it to our case to show that that this thing really does have a sustainable error correction threshold as you repeat rounds of stabilizer measurement, noise channels, and recovery. But I'll get into the meaning of these symbols a bit later on. And then we'll also talk about some unpublished stuff, which is a work mainly done by Joseph Iverson, which you can actually details of this are in his thesis if anyone's interested. So I can point to that, and that's talking about how to do universal gates with this subsystem toric code. And there's actually a few options of how to do that, but this particular realization is sort of based on the tetrahedral color code, I would say. That's how I understand it. Okay, so let's just get into it. Okay, so just to review some stuff, subsystem codes, probably people are familiar with, but they're some kind of, I'll just go over it again just to make sure. So subsystem code is a generalization of a stabilizer code, and what you really, one way of thinking about it is you have some stabilizer code, and you say that some of the logical qubits you're not going to care about encoding information with them, and you kind of denote them as these gauge qubits. And I don't know, I always thought this sounded like a slightly strange, like, why would you want to do that? But it turns out that you can sort of measure the logical operators of these gauge qubits, and these become your gauge operators, and we'll see why this is something you might want to do. And I mean, maybe what, so the pros of doing this is you can, in some sense, the useful versions of these subsystem codes are ones where you can break the stabilizer up into smaller operators. So this is like good because you want to always measure small operators rather than big ones to get better performance. And also another reason to consider these codes is just some of the no-go results that have been proved for various stabilizer codes just don't apply with this change. So it's possible that we can avoid some of the restrictions we have when designing codes. So our code is so it's just based on the cubic lattice. So you can see here we've got the cubic lattice, and importantly you can bicolor the cubes like this, so in this checkerboard pattern, and we're going to put our physical qubits of the code on the edges. Then we have gauge generators that look like this. So for each red cube, we're going to have these 8 operators, and you can see they're sort of associated with the corners of the cube. Can you see my mouse, by the way? Yeah, okay. Yeah. So you see, like, for example, we have this cube and this vertex, and then this gauge operator is going to be the 3 edges that contain the vertex and are themselves contained in the cube. You define stuff like this, and then similarly for the blue cubes, you get your Z gauge generators. And there's also some extra gauge generators we include on the boundary. So this is maybe seems, I'll just explain where these come from because it might seem a bit strange. So you've got 3 different types of boundaries here. You've got like these ones which are kind of similar, except one's X here, one's Z, and then you've got the top and bottom, which kind of look like 2D toric codes themselves. And I can just talk about how we constructed these boundaries, because this code is actually based on, we're using this picture here, but it's actually the way we found it is when you consider various kind of toric codes on 3D lattices, there's one that I was looking at some stage. So you can consider, and this code came up in when you want to construct a transversal CCZ in the toric code. You can't actually use 3 of the same lattice. You have to use like the standard cubic lattice, and then you use these other 2, and these 2 are defined on some other tessellation, and it turns out that these are what you use to generate this subsystem code. And this blue boundary here and this red boundary are kind of like the rough and smooth boundaries of them. So although they kind of like, it's kind of like, where did they come from? Actually, if you kind of look at it in a slightly different picture, these are very natural because they just correspond to kind of rough and smooth. And these top ones are the more weird ones. So we found that what we're always wanting to do. So the important thing is the stabilizers here are identified with the cube. So we have, let's say this operator here, I've told you how to construct these gauge generators. And then if we want to construct the stabilizer, it's just a 12-body operator acting on all the edges of this cube. And the important thing that we always want to be able to do is, the single shot error correction to work, we have to be able to reconstruct the stabilizer generators from 2 independent products of gauge generators. So we can do that here. For example, you see, I could take this one here, this one, and this one, and this would, product of those 4 gauge generators would give me this weight 12 stabilizer. But I could alternatively take like this one, this one, this one, and this one, and it would give me the same operator. And this is important for the single shot error correction. And so at the top here, we've got this strange thing where we've got these extra qubits living here. And this is again, the reason we're including these is because the top of the lattice, we're kind of cutting through a cube in half, but we still want to be able to reconstruct the stabilizer associated. So this is actually going to be a weight 8 stabilizer. And we still want to be able to construct this from, wait, it's actually, maybe it's going to be higher because of, yeah, no, I think
where does the 8 come from?
No, sorry. So there's going to be actually, I think it's going to be weight 10 because there's this one, there's like, it's like half a cube and you cut through here. So you're getting these 4 and then you get 4 qubits on the kind of base, but then there's these extra ones here and there's also going to be another extra one here. Okay, so it's going to be 10.
Thanks.
But we still want to reconstruct this from 2 independent products of gauge generators, which is why we add these strange things here. And this pink edge actually is telling you, so this is going to be a weight 2x, and also we're going to include a weight 2z on these 2 qubits. So sorry, like these tubes just correspond to, this would be like ZZ, this tube means that, and similarly this would be like XX. And we include these because we always want to be able to reconstruct stabilizer from different products of gauge generators. And it's kind of interesting to contrast this with the gauge color code, because in that case you have like this tetrahedron and you sort of get this for free, although you have to also be careful that the colors on the boundaries are right, but you get this property without having to sort of introduce these extra qubits. But we struggled for a while to like construct some lattice that works, and then this is the one that we came up with. But maybe there's like a more elegant way of doing this, I don't know. And actually we do have actually some, you can actually do a thing where instead of having these rough and smooth boundaries, you can like identify them. So you'd identify like this boundary and then this one and then this one and then the back one, and then this would give you like a torus times an interval kind of thing. And this code would have 2 logical qubits, and yeah, it was but we kind of realized this later on. So that's maybe simpler.
Can I just quickly interrupt with a probably naive question?
Oh, please, yeah.
I don't understand the topology of the torus here. Like, where's the periodicity here? Is it a 3-dimensional thing?
Yeah, sorry. So okay, so this picture here is just like a cube. There's no torus here. Yeah. So this one is just like this is like topologically, it's just this cube, and then we've like this tessellation on it, and we define these operators. This is like a purely 3D thing. I was just saying that these boundaries are kind of so there's actually an interesting point about these subsystem codes, is that if you, let's say we had a 3-dimensional, we're in a 3D, and we want to, for the example in the toric code, you can define a toric code on a 3 torus, and it will have some number of logical qubits. But if you do the same thing with the subsystem version of it, so if you did use this subsystem toric code and you defined it on a 3 torus, it actually has 0 logical qubits. And this is the same behavior you'd see for the gauge color code as well, which is so that's it. So you have to have the boundaries if you want to encode logical information. So then there's a choice about exactly what boundaries you want to take, because you have some options. And we show kind of one option here, which is we're going to have a cube as our actual, and then have a tessellation of a cube. But all I was saying is that you can take another option where you imagine you take, you could identify this right boundary here with the left boundary, and you could identify this front boundary with the back boundary. So that is but you retain these top and bottom boundaries. And so you can look at this as another option, and this actually has 2 logical qubits, so it's somehow more efficient as a encoding. But you know, in some sense, you're then losing the ability to engineer it in purely 3D because you've got these periodicity. But you have to actually introduce a boundary somewhere if you want to have any logical qubits, and it's the same for the gauge color code.
Is the reason that you need the boundaries? Okay, I'm asking a question about a paper you may not have looked at. Is the reason, is the code that you get if you did put it on periodic boundaries the same as the the recent dynamic logical qubit paper?
Oh,
Is it the same? Like is the
What
reason
paper is that?
the Han Hastings and Hahn.
Yeah, okay. Mhm.
Yeah. So I mean, to summarize my understanding of what happens there, if you just take their code and just treat it as a static code, you basically get, I mean, it's a gauge description of a toric code essentially, but what you're going to get there, the key thing is that your stabilizer group has the logicals in it to start with, like it has the ribbons, right? Which is why treated as a static code, it doesn't have any qubits. Is that what happens here? That you like the objects analogous to the ribbons in the original toric code are in your stabilizer group? Is that the?
yes. So I haven't actually read the Hahn Hastings yet, but this sounds very interesting because maybe this could be operated in the same way. But yeah, you're right in that the reason this doesn't have any, if you include the periodic boundaries in all three directions, X, Y, and Z, then what you end up having is, yeah, the things that are going to be the logical operators of this code are these sheet-like operators, basically. These are the bare logicals, so the ones that commute with the gauge group, and they are in the stabilizer if you don't have boundaries.
Yeah, this sounds like, I think I mean, maybe there's a detail I'm missing. It sounds like you could probably use these generators to in pretty much exactly the same way. Like the trick there is they start with a gauge description that inadvertently also contains the ribbons, therefore doesn't have any qubits. But then by measuring things in a careful way, you basically you get this instantaneous stabilizer group thing, and you effectively get the same stabilizer group, but it just happens to miss the logical. So you actually have qubits. So I wonder, maybe there's a technical reason you can't do that here, but it seems to fail it seems to fail in the same way. So
yeah, okay, very interesting. I will look at this Hastings paper and get back to you on that because I mean they're using this it's like the honeycomb model, is that right? Something like that. So they have like X, Y, and Z terms, but does it matter that they have them? Is it, or is because we'd only have X and Z terms here, but that probably is that a barrier?
It might. That's not that's one reason it may not be. Maybe, I mean, your things are failing the same way. Maybe you can't do this dynamic stuff to fix it. In your case, I mean, in their case, like they don't really describe the construction all that explicitly, but they're sort of exactly where they get the Y's from is not
okay.
Maybe you could do a similar thing where you like you grow it onto a bigger lattice or something. And
I'll have a look at that with this in mind, because I think it would be very nice to realize it with this periodicity, and it's maybe like in 3D you would gain something that you wouldn't get in a 2D example. I don't know, but thanks for that.
Well, it's why important, because maybe in the 3D color subsystem code you can, like there you have X, Y, and Z stabilizers, right?
For which one?
In the 3D gauge color code. You measure exactly the same.
Because you
might as well measure Y.
I don't know. I just
I
have no idea why I hope it isn't important, but I don't know if they needed some symmetry to do what they did. I haven't read the paper at all. I just looked at the abstract.
Okay.
Okay, cool. So so this code I'm showing here, this picture, this has the parameters we've written here. Like the bulk term is the important one. So you just gain like L cubed and number of physical qubits that is, then you have one logical qubit, and the distance is like L plus 1. So in the subsystem codes, this is like what I've written there is the dress distance. So you have these two distances where the bare logical operators are the ones that commute with the gauge group, and so these would be like these are sheet-like objects, so you can select them on this kind of boundary, for example, or this boundary. But then you're allowed to multiply your bare logical operators by gauge operators to reduce their weight, because that's still going to have the same action on the logical subspace. And if you do that, you can reduce them down to line-like operators, to string-like things. So, for example, it would run like this across, and that's where the D is coming from. That's talking about the dress system. Oh yeah, okay, that's just what I said. Cool. Oh, okay. So now there's like an aside, but just to and maybe Chris's comment might solve the need to do this, but we have this. We wanted to construct a code where all the gauge generators were all weight 3, and this is because the main reason is this is, you know, if you're considering a noise model. A circuit level noise model where you're extracting the syndrome with like a C0 circuit, then we want a situation. The good thing about having a weight 3 operator is, you know, a weight 2 error on this is equivalent to a weight 1 error. So you can't get any of these so-called hook errors that you can get in the 2D toric code, where one fault in your syndrome extraction circuit can propagate to a weight 2 error on the data qubits. And so, you know, the absence of these hook errors, we'd expect to improve the fault tolerance threshold of this for the circuit level noise, and that's actually something we're planning to look at. I'm writing code for this at the moment, but we hope that, I'll show you later some numerics, but we hope that including kind of circuit level noise is not going to degrade the performance too much. But yeah, we'll see if that's the case. Yeah, so there's this issue in the code I showed you in the last slide where. So this is like the top and bottom boundary, and then so we have, this is showing the gauge operators. So you've got these like weight 4 X operator here, for example, and weight 4 Z here, and you know, this is just like looks like a 2D toric code. So we wanted to find a way of reducing the weights of these weight 4 operators to make everything weight 3 or smaller to avoid these hook errors being able to happen. And the nice thing is there's a pretty standard way to do this, which has been there's this paper by Bravi and others, and also this recent work by Higgett and Breukman, where you construct this 2D subsystem toric code, and so you can kind of split up these weight 4 checks, and you end up with these weight 3 checks instead. And what we actually did is so it kind of, you have to introduce these extra ancilla qubits, which I've shown here, and then you implement some constant depth circuit, which is then gonna what it's going to do is it's going to transform the gauge operators, and then you find you can pick a generating set like this. So, you know, we've got these weight 3 X term, weight 3 Z, and we also have these like weight 1 operators here. These are fine because these are gauge operators, so it's not like having a weight 1 stabilizer or anything. And you know, so this ends up, you can reduce the weight of all the gauge operators so that everything is weight 3 or less. And at the cost of introducing some ancillas, but this allows. We think this is probably the setup you'd want to use to do circuit level for the actual implementation with circuits, because, you know, then no hook errors can happen, and you don't pay that much of an extra cost in qubits. And yeah, this top thing is basically like the 2D stabilizer toric code, and it's nice because you can sort of see that this subsystem code you have. On the top and bottom boundaries, you have like the 2D stabilizer, a 2D subsystem toric code, and then you have this 3D bulk, which is sort of giving you the single shot error correction, is how I understand it anyway. Yeah, so that's like a little aside, but it's just a thing to show that this can be done. And also there are like probably other ways of. This is just one example of how you could do this. But I think maybe there might be a smart way of doing it. Who knows? Oh yeah, and just to like. Just to emphasize something, is these 2D subsystem toric codes are sort of like stabilizer codes in disguise, because you can do this, you can do a constant depth circuit to map the 2D stabilizer toric code to the 2D subsystem toric code. Whereas I don't think you can actually do that with this 3D subsystem toric code. So it's not like, it's actually it's so what Alex said here, the first genuine subsystem version of the toric code. So it's not something that you can do a constant depth circuit to map to a stabilizer code. It's really something different. Okay, and so that was like a specific model, but there's also a general construction that we introduced, So it's a slightly more involved, but it has kind of similarities to other pictures of both the color code in the dual lattice picture and also this picture of the toric code, which is used by Thomas Joachim O'Connor and Ted Yoder in their paper. They look at similar things where they look at octahedra as like a fundamental object. So we're going to get some lattice like this, where we have qubits on octahedral volumes, and we need to have some special coloring of the vertices. And then there's like gauge operators associated with edges. So by that I mean, if you have a gauge operator associated with an edge, you just act with, let's say, X on all the octahedra containing this edge. And then stabilizers, similarly, if you have a stabilizer associated with a vertex, like an X stabilizer, you'd act with X on all the octahedra containing this vertex. And you can as I said, you need boundaries. So you can actually consider like a closed, like a tessellation of a closed manifold, and then you can like remove one of the octahedra to create some boundaries. And we show that this is like a standard, another way of constructing what we have. And yeah, in this picture, it's also easier to see that you can recover 3D stabilizer toric code by kind of fixing the gauge. So with these subsystem codes, we can, the gauge, we don't actually care what state the gauge qubits are in, but we can, if we choose to, fix them to a certain state. And if we do that, we actually end up being we end up having something equivalent to a stabilizer toric code. And the way you could do this is so it's like you'd measure all the Z gauge operators and you ensure that you're in the +1 eigenstate of these. So, and then it's like they're the stabilizers of a 3D toric code, and then you'd recover the 3D toric code. And the nice thing about this is so we have a procedure that, just given an arbitrary lattice, you can change it into this some octahedral lattice with the right colorability properties. So it's just a general procedure, and basically for any lattice, you can make it a simplicial complex where the simplices are like associated with the flags, and then from that it's easy to change it into an octahedral lattice. So this gives you a way of constructing more kind of codes which have the same kind of properties, but we only really looked at the one, which is the one I showed you last time. But we wanted to include this to show that it's sort of a more general thing than just this one example. And the nice thing is also we have a construction for this in higher dimensions. So basically this stuff just generalizes, and you can take a hypercubic lattice and you can build gauge generators in a sensible way, and you have stabilizer generators. And the nice thing is the gauge operators are always weight 3, although the stabilizer weight will increase as you go up higher dimensions. And there's a really nice example in 4 dimensions actually, which is because you end up with a very, very symmetric thing, and it actually, you can gauge fix it to the codes that Thomas and Ted ended up with to get a 4-dimensional toric codes with a transversal control Z gate. These are actually gauge fixed versions of the 4-dimensional subsystem toric code. So there's some like unanswered questions here which I'm kind of interested in for these high dimensional cases. So one, can you gauge fix the 4-dimensional subsystem toric code to the self-correcting stabilizer toric code? Because the ones that Thomas and Ted consider for the 4-dimensional CCCZ are not self-correcting, because to get a 4th level Clifford gate, you have to have like the most imbalanced logical operators. So one has to be a string and the other one has to be like a 3D membrane thing. But if the self-correcting toric code in 4D is the one with the balanced logical operators. So both logical Z and X are 2D sheet-like operators. And I'm not sure, maybe it's impossible, but I wanted to know if you could gauge fix this this subsystem toric code in 4D to the self-correcting one, because it'd be very nice if you could, right? Because if you could gauge fix to like the ones with the logical gates, you can do the gates there, but then most of the time you can just stick in the gauge where you're in a self-correcting quantum memory. But I don't know, maybe it's impossible to do this, but I was trying to work it out and I didn't manage to yet. But that's that. And another interesting thing I think is so anyone familiar with the gauge color code? There's like, so as you go up to higher dimensions, there's like different choices you can make about what to associate your gauge operators with. There's this nice and in this paper that Alex and Michael Bevelin wrote, there's this nice like triangle where you basically so you have the gauge color code in the dual lattice picture, you have some simplicial complex, and then you're going to associate X and Z gauge generators with like edges, for example, or like volumes or vertices, and there's all these choices you can make, and each one will give you some kind of color code, and certain choices will give you a stabilizer one, certain one will give you a gauge one, but they have this kind of quite big range of things you can build. And in this toric code case, we only sort of know the extreme points, so we can construct like the stabilizer versions and like this subsystem version, but there's like this whole other region of codes that we know exist for the gauge color code construction, which I don't know how to make them for the subsystem toric code. So yeah, this is something we had some ideas about how to do this, but it never actually worked out. So but this is something I'm still interested in solving at some point. Yeah. Yeah, and as yeah, so this is again, this is this construction, general construction is reminiscent of the gauge color code. Okay, so that's kind of the definition stuff out of the way. We can now talk about error correction procedure. So let's just consider, for example, X errors. So we measure to detect these. We did measure the Z gauge generators. And the important thing about these things is that they have to satisfy these local consistency checks. So, you know, the product of all the gauge generators in this, which are kind of in this cube, has to be the identity. And also importantly, the product of them around the vertex also has to be the identity. And this is going to give us what we call some kind of Gauss law. So it gives us these consistency checks on the syndrome of the gauge operators. Yeah, so we're going to call a gauge flux just a -1 measurement outcome. So we're going to try and understand what happened, the structure of this gauge flux. Yeah, so actually what we end up using for this error correction picture is a dual lattice to the one I showed you. So sorry for changing the picture, but we think it's like indispensable for understanding how this works. Mm-hmm. So what we're going to have is we have these we're going to have blue vertices at the center of these cells. So, you know, then we're going to take vertices also for these. Okay, so it's not exactly the dual lattice, but it's a lattice you can construct from this from this one I presented. So what we're going to have is blue vertices at the center of these cells, and we're also going to include vertices for the original vertices of this cubic lattice. We're going to color these like green and yellow. So these are the relations, and then we're going to have edges that can correspond to Z gauge generators and also edges that correspond to qubits. So I think, oh yeah, okay, here we go. So you can sort of see what's going on. So, oh, okay, let's do this again. Yeah, so we have this blue cell here. We're gonna put a blue vertex here. We're gonna put vertices where the vertices of this gray lattice are, and we can bicolor these in green and yellow, and we're gonna connect them with edges. So this is gonna give us there's gonna be an edge from this vertex to the vertex going to put the center of this cube, and that's going to uniquely pick out this gauge generator here. So these edges correspond to gauge generators, and then we're also going to make edges for qubits as well. So yeah, you can see this is like what we're going to, I think, call like flux graph or something along those lines. And you have this structure where so these blue vertices are like the stabilizer generators, and these green and yellow ones are what we're calling relations. So these are points where, yeah, this sort of Gauss law has to be satisfied. And this, so when you do this in what you find is that, so those consistency checks I showed you, where, you know, the gauge generators in a cube or around a vertex have to multiply to the identity. This means that for a flux configuration to be valid, it's got to form a closed loop like this. so for example, here's like an example of what would happen. And this is what we use to diagnose measurement errors, because basically if you measure your gauge flux, and then if you find broken loops, you know that this can't happen. So then what you do is you just close the loops. So what we find, the reason we introduce these colors is because you will get an error. So you get a non-trivial stabilizer. So a stabilizer is unsatisfied if the gauge flux at this vertex changes color. A
question: Can you say more about what this precise Gauss law is like? I mean, it's like a relation syndrome of the flux must be vanishing somehow, right? But what is it precisely?
So all it is that so like that you write down some kind of sets of linear maps to describe this, and exactly, it's like the relation syndrome of the flux must be zero. But what's saying is at each of these vertices you have to have the gauge operators containing each of these vertices here have to multiply to the identity. And what you can show that means is that, you know, the parity of the unsatisfied of these gauge flux edges which have -1 outcome, the parity has to be even. So this means, you know, that the loops have to be closed always.
Okay.
So you can just derive it from the product has to be identity, means then you can show that the parity has to be even.
Okay, thank you.
And so you have this structure where you have these closed loops, and then it turns out that when you have a -1 stabilizer generator outcome corresponds to where the flux changes color. I mean, you can again show that this will be the case just by kind of looking at the examples. And then so what the structure of the error correction is this: you have so if we want to, let's assume there's no measurement errors, for example, just to start with, then when we measure the gauge flux, we'll see loads of closed loops, but they will have points where they change color, and this tells us where the stabilizer -1 outcomes are. So for example, here it's here and here, and then we can then the error correction problem is like matching in a 3D toric code. So then all we need to do is just find the shortest path between these blue dots to give us the correction.
Mm-hmm. Okay, wonderful.
And now I can tell you about the single shot minimum matching decoder. So yeah, in the general case, this is what you'll see. So this is just a cartoon using the kind of colors and the structure of the last slide. But you know, we've got these loops here, and these flux can change color. There's only 2 types of color, and then but in general they're going to be broken because you know, we've got measurement error, so we measured the wrong thing. So in general we have these loops, but they're kind of broken up. And maybe one important thing actually is that you know, you always because you're when you measure, it's not like a stabilizer code. You're always going to observe some like soup of loops because you know, the gauge operators don't always commute with each other. So you always observe this even in the no error case, you'd still see these loops of gauge flux, but you just wouldn't see them changing color. But in this case here, where there's measurement errors, they're all broken up. So what do? We just need to close the loops to make the gauge syndrome valid. So to make it such that it obeys all those consistency checks, which we, you know, call the Gauss law. So first, yeah, we close the broken loops, and then what we can do is from the places where the flux changes color, that gives us an estimate of the stabilizer syndrome, and then we just do minimum weight matching again on this thing. So this would look like this. So yeah, you see, we've closed like this loop here, and we've closed this here and here and here, and now we can estimate what the stabilizer syndrome is, because it's just exactly where these loops, where the color changes. Oh yeah, and here I'm just showing that in this model with the boundaries, you know, the loops don't have to be closed; they can terminate on the boundaries, but in the bulk they have to be closed. But that's just, you know, very similar to for example, the 2D toric code. And then for these, so we can close these loops. It's just a minimum weight matching problem. And we find these stabilizer -1 outcomes, and then it's again a minimum weight matching problem just to find the shortest path kind of on qubits, linking them. So you know, then you can just look at this problem, and then you just do some kind of thing here where this is just a the correction. And this is like showing you again, you can sort of you can bring this charge to the boundary as well. So it's, you know, you have pairs in the bulk, but you can have single things that you take to the boundary. And yeah, the nice thing is in this kind of picture I was showing in the last slide, like both these steps just reduce to pairing up vertices in some graph. So we can just use minimum weight matching for both steps. And the other thing that's nice is, you know, I think you could use other 2D toric code decoders. I think you could probably use union find. I don't see why not, but I haven't looked at that in detail, so maybe you can't. But the nice thing is the minimum weight matching algorithm generally has good performance, although it's not the most efficient thing, but it's better performance than previous stuff people have used for the numerics for the gauge color code, for example. The only other stuff that's been done was using RG approaches, which generally have worse threshold. And also,
so there's nothing speaking against using matching in the 3D gauge color code, right?
Yeah, you could use like restriction decoder, right? I assume it would be fine.
Sorry, a very naive question. Sorry, I apologize. But I mean, the heart of the matter is, I mean, you do the syndrome extraction in the single shot decoder setting, but then the minimum weight perfect matching decoding is basically used as it is commonly used, right?
Yes. Yeah, so the I think the thing that's like, you're right. Like this final step is just like standard decoding. The thing that's good is that we can do the flux validation, or the step where we repair this broken up flux can also be done with minimum weight matching. Mm-hmm. That's what's useful here. So like both steps can be done with the same algorithm.
Okay, that's helpful. So okay,
but yeah, the second step is just like totally standard toric code decoding. Okay, but the first step is something we can
good.
Matching, which I wouldn't know how to do with, unless I think you probably could use matching, as Marcus said, but you'd have to use this restriction decoder approach. So it would be more complex, and generally, like, I think the performance would be worse than this. And the other nice thing is that we have this algorithm which we use numerically, but also we can prove the threshold for exactly this algorithm as well. So that's kind of satisfying. And just to say that there's for this, when we have the noisy measurements, after each round, it's likely there's some residual error left, but what we care about is like how quickly does this residual error grow? Is it still under control as we repeat noise and error correction? That's what we really want to understand for kind of the performance of this thing. Okay, so I can now tell you about the numerics. Let's consider IID, Pauli X, noise, and measurement errors, all with rate P. So each qubit independently has a X error applied to it with probability P, and each gauge operator outcome is flipped with probability P as well. So we're going to look at how errors accumulate during repeated rounds of QEC, as I said. So each round, what we're going to do is have a X errors on all the qubits, IID noise, and then we're going to extract the gauge operator outcomes noisily, and then we're going to use this single shot minimum weight matching decoder, which remember has like 2 rounds. First, we use minimum weight matching to validate and repair the syndrome of the flux, and then that gives us the stabilizer syndrome, which we then can just correct in a standard way using minimum weight matching. So, for example, and the number of error correction round we're going to denote by T. So this is the data for like T equals 4. So you see this nice kind of threshold behavior. And then what we want to understand is like, how does this threshold change as we vary T? So yeah, in this plot, we've got the physical error rate here, and then this is the failure error rate. The threshold is this intersection point, and we actually estimate this using standard finite size scaling. And then what we're going to do is like, we want to understand how does the threshold change as we vary T, because in the past you've seen stuff where, at least in previous work I know about, where you have like a reasonably high threshold maybe for and the 0 case here is no measurement error. So this is like the code capacity threshold. So you have like a high value and then it kind of decays down. But the really interesting thing about this code is it seems very insensitive. So I mean, okay, we've only gone up to 8 rounds here, and we probably maybe push this a bit further in future work. But from what we can see, the repeated rounds of error correction, noise, and recovery really isn't changing the error threshold, which is, I think, this was definitely something that was surprising to us. Like we were expecting it to drop at least some sense, but within our kind of numerical accuracy, it doesn't seem to have changed at all. And it's stable at about 1%. And as I was saying earlier, like with these weight 3 gauge generators, we want because there are no hook errors, we think that hopefully this won't change too much, even when we include circuit noise. But this is more of a hunch at present, and we'll have to. I think it will probably drop a bit, but I don't think the thing is the structure of the noise channel shouldn't really change. It's just like the effective value of P would change, but I don't think the structure of the noise would change. Anyway, that's something that needs to be confirmed with. So okay, and one other thing.
There's no code capacity case at all.
Yeah.
Ah, okay.
Sorry, what do you say, Joshua?
Oh, there's no change from the code capacity case when you introduce more measurement errors.
Yeah, so it seems to be just the same when you include measurement errors. So we were really surprised about this. And we also looked at so there isn't the data here, but in the paper we looked at the sub-threshold scaling. So below the threshold, you expect your logical error rate to go like P over P threshold raised to the power of like alpha times L to the beta. Where alpha and beta are like fitting parameters, and you expect this. So the distance of our code is like L, where it's because it's an L by L by L lattice, and then we expect it's like P over P threshold to the raised to the power of alpha times L to the beta. We expect beta to be around 1, and then alpha is something. And what we did is we looked at how these change with as you vary T, the number of error correction rounds as well, and we saw that they're also stable. So not only is the threshold not changing, but the kind of suppression of the noise below threshold is also stable, it seems. Again, this is only for not too many rounds, but it looks promising. And of course, like the logical error rate the probability of a logical error is going up as you increase the number of rounds, because that's like inevitable. But the nice thing is like the suppression of logical error rate by increasing L is like the same, and the threshold is the same. It's at least from like, so we can't actually like this. We can't prove that this should happen. That this like the code capacity and this kind of phenomenological noise model threshold should be the same. But it's very like, but from the numerics, it does seem to be pretty robust. So that's quite nice, I think.
Is there anything special about measurement errors compared to other errors, compared to the more standard setting of decoding? Or?
You mean like in this case, or just like generally?
Oh, in this case, in this case of like, in this single shot framework.
I think the noise model is like the same one that you would use. So like we tried to make it comparable. So the 2D toric code, like the equivalent figure is about 3%, I guess, because this is the error model. You have data qubit errors, and you have like each syndrome bit is split for probability P, and this can be reduced to matching on like a 3D cubic simple cubic lattice, and the like optimal performance of that is like 3% or so. And then the next step is to do the circuit level noise, where the toric code threshold goes down to about 1%. So we're hoping that for our case, we're lower than the toric code for the kind of equivalent noise model, the 2D toric code. So for this phenomenological, what I'm going to call phenomenological noise, where you have like bit flips of probability P and measurement syndrome bits flip of probability P as well. Yeah, our threshold is about 1%. The 2D toric code with repeated measurements is about 3%, but I hope that the circuit level performance will be similar, because ours won't suffer as much from these hook errors. But this is something that needs to be.
Wonderful, thanks. Great.
Thanks.
How much? What's the error rate on the stage 1 of the decoding? So the syndrome fixing, is that, given that it doesn't change once you start ramping up the number of cycles, is it that the stage 1 decoding is perfect or near perfect, or is it just
Yeah, you mean, so, oh yeah, I should have said that, like, after we've done the teeth round, we then do a round of perfect error correction just to, like, actually get a logical error rate out. But that's like a standard assumption. And this is kind of like, you know, like operating in a quantum memory framework where, you know, you imagine you measure out all your qubits at the end, and you just use classical error correction. So you don't need to worry about measurement errors there. But yeah, the logical error is like increasing as we're increasing the number of cycles. The problem is the logical error. But it's
compared to the confinement paper we wrote, where we found that basically the bottleneck was in the syndrome repair step.
Yes, I think what this is showing is that is not the case here. The bottleneck is like the syndrome repair step is good, and the bottleneck, like the other thing, is the actual the threshold of the matching problem on the stabilizer code, because there's also, like, Alex did some StatMech, and I think the optimal value of the threshold for the kind of second step, which is the you know, the stabilizer code part, is actually around about 1%, maybe a bit above. So I think the minimum matching is getting close to optimal there, and I think that really is the bottleneck. And yeah, this actual syndrome repair, flux repair step is doing pretty well. Yeah, so it's actually different to our case, because they're in our paper, Joshua. Yeah, we were limited by the syndrome repair, right? So,
yeah,
interesting.
So one of the things, have you done these similar simulations to the Z errors as well?
Yeah, so the Z error is like completely analogous, because you just you know, because it's CSS, so you can just do everything. It would just be the same problem. So we only actually simulated like X errors, but you know, you could do like a general channel, and then you could just correct both separately. So if you had like IID X and Z noise, the threshold would be the same, although the logical error rates would be different.
Yeah, I guess if you were to do depolarizing noise with X, Z, and Y errors, you'd get a higher value for it would be the same threshold, but the number would look bigger. But
yeah, I think like that's also something that we might want to. Yeah, that we haven't actually done any depolarizing noise simulation, and maybe this, like, I know in like the 2D toric code, there's clever stuff you can do with like the correlations between the two things to take into account the Y errors, and maybe to improve the performance. But that's not something we've actually looked at in this case. But yeah, it's kind of again, it's interesting, like, to think about what's the optimal performance of this for this decoding problem, especially the noisy measurements, and how, like, I think we're probably doing pretty well, but I don't have a good I don't have a good grasp on exactly what the optimal value of the threshold is for this noisy decoding problem. I don't know how to estimate that.
Interesting. Thanks.
Okay, cool. So I can run. Oh yeah. So sorry, Jens. Just to check, we're already like an hour. Is it cool for me to continue, or should I wrap up?
No, I mean, you shouldn't wrap up now, because I think now is the cutest part of your paper, right? The proving signature correction. No, go to this. I mean,
Okay.
don't push it to like 5 hours or something.
Okay. Just yeah. No. This is like
argument we want to hear.
Okay. Cool. Okay. Yeah. So I'll tell you a bit about the proof now. So this is a very inspired by Hector's work. Got his really nice results in this area, and you know, he proved that single shot error correction would work for the gauge color code, and also slightly more general setting. And yet you need this notion of sort of slight generalization of a IID noise model to this. So we're going to call it P bounded. So we've got a subset of locations where you can think of these as kind of like qubits, or they can also be like gauge operators. And then, you know, so the probability of errors affecting things that are subsets of this set A is exponentially suppressed in the size of A. So this is saying that, you know, these are sometimes called like local stochastic noise as well, I think. but it's saying, you know, that you are allowed, it's not like IID, you are allowed to have correlations, but they can't be spread too far over into large area kind of thing. So it's like a slight generalization, but allows you to capture more noise. And this is the noise model this is the kind of essential property of the noise model we need to prove the threshold. Yeah, and so what we have is this recovery channel, R sub eta. So this is like a single shot Minimite decoder. And then what we're going to do is we assume that the measurement errors that are happening are going to be eta bounded. So when, you know, to do this recovery, we have to measure the gauge operators, and then we're assuming that the measurement errors that can happen during this process are eta bounded. And then we have a noise channel as well. So this is going to be Pauli X errors, and so the slight technical thing, we need that this noise channel is equivalent to a noise channel that is tau bounded, and this is a slight annoying technical thing, but is necessary for the proof. And also this epsilon is telling you that the logical failure rate of if a noiseless Minimite matching decoder was run on this noise, the logical error rate is at most epsilon for this channel. And then this is theorem here. So
sorry, before you continue, did I miss this? Like, how can you have correlated errors?
Oh, okay, yeah, sorry. So
if uncorrelated errors, then I can clearly get the logic of the argument. But otherwise, I mean, if you have arbitrary correlations, so how can you ever get an exponential bound of some sort?
Oh, so you can't have arbitrary correlations. Sorry, so you shouldn't say really, but you can have correlations like on a short range on like. So for example, I think
that you can kind of cluster and then have a bigger coarse graining picture, so that
yeah,
on that level,
so like
the idea again.
Yeah, for example, in one of Chris's papers, they look at nearest neighbor correlated errors or something like that. And I think something like this you could write down as a p-bounded error model. So it's definitely not arbitrary correlated errors. That's true. But as long as they're kind of geometrically local, small scale, then you can, yeah, as you say, like coarse grain, and then
arbitrary errors, of course not. I mean, clearly you can always back engineer anything you do and find some error that would just
like,
that's for sure. But I mean,
apply a logical operator.
That's no. But I mean, even like too long range correlations or so much.
Yeah. So it's got to be short range. Yeah. But it's just a nice way to sort of capture something a bit more general than IID that you can. I think like a lot of the time, the stuff you can prove for IID, you can also prove for these type of channels. So the main theorem is about like so if we apply, sorry, this kind of green thing is moved weirdly, but if we apply a code space projector here, and then we're going to apply the noise, and then we're going to apply the recovery. So as long as eta and tau are small enough, exists a tau prime and eta prime, and sorry, not eta and tau are small enough, there exists a tau prime and an epsilon prime, such that this is equivalent to applying the code space projector and then applying the noise. And the important thing is that we have control over the values of tau prime and epsilon prime. So I'm not sure if Alex has written this here. So this is the important thing, is that the residual noise is suppressed if the measurement errors are suppressed. So this is like, as we said before, what is so tau is like telling you that's about the tau bounded errors. So if we reduce the measurement noise, which is captured by eta, then this is kind of tau prime is telling you about the noise left over in the system, and this can reduce this arbitrarily. So we can make this 0 by just reducing the measurement error rate. And then also, so obviously we can't completely remove the noise from the system. The important thing is that as we increase L, so the size of the code, we can make the failure rate after applying our recovery operator is the same as the failure rate that would have been if of this so we haven't increased the probability of failure at all. It's just, which is sort of like the best you can do. And in the general case, you know, as for finite L, we've got like control over how epsilon grows. I think it grows like linearly. So it's just like a multiple of epsilon here. So, you know, you're always, for finite L, as you repeat rounds of error correction, there's always the probability of logical failure is going to increase unavoidably. But the thing is that it increases in a very slow, benign way. So that shows you that, you know, error correction over repeated rounds is possible and will work. But, which is that's like really the important content of the theorem. And yeah, so then there's like this. So as I was saying, so you repeat this process. So we're going to apply a code space projector, and then we're going to apply noise and recovery, and we're just going to do this 10 times, and then we can show that, you know, what this is going to be. It's the same as applying the code space projector and then applying a noise channel where residual noise is staying tau bounded, where I have control over this, and decoding logical failure probability is just going to grow linearly in n. So, you know, if this logical failure probability to start with is very small, we can do many rounds of error correction before the probability of a logical error gets anywhere near significant, which means, you know, you can this is all for like a quantum memory case, but you hope that this would this would be retained when you're doing gates as well, as long as, you know, you're designing your gates in a type of way and make sure everything's fault tolerant. Yeah, and yeah, so to prove this, yeah, I mean, so the details the gory details are all in the paper, but it's all about these channels, and we have to basically, it's all about proving these what happens to tau prime as a function of eta and epsilon prime. And we can, and the nice thing is, as I said, is that we have this single shot minimum weight matching decoder, and we actually, it's quite a nice thing to analyze, because you always have, like, you know, a guarantee that if an error occurs, then the correction is always like smaller weight than the error, or the same. So it's a nice algorithm both for us to use numerically and to use in the proof. Yeah, so I think that's it. I mean, yeah, okay. So yeah, as I said, the residual noise does not accumulate in like an uncontrollable way, and you can repeat this many times. Are there any questions about this? I can also.
Yeah, I had a question on your previous slide. Maybe, well, okay, first a more naive question.
Yeah.
When you're increasing the lattice size to infinity, does the error have to converge to a fixed epsilon, or could it increase with each increment in your lattice size?
Yeah, so we can. It's going to converge to like this fixed epsilon, which is given by this original noise channel here, which is like, this is like the noise, describing the noise, your physical noise channel. And I can't remember exactly what the expression is, but let me just, I can have a look in the paper. Okay. Yeah, so where is, okay, yeah, so epsilon is going like, yeah, so it's going just, epsilon prime is like epsilon plus some function of tau, basically. Where tau, this function of tau is like, yeah, maybe I can you see this PDF now?
Yep.
Okay. So this is the actual more technical statement. So this epsilon here is going like, this is the epsilon of your noise channel, then you've got your function of tau and tau plus tau prime. So what is F? It's this. So this is like, you know, a standard thing you get from these threshold proofs. So, you know, this is like an error rate, and this is the threshold error rate, and you've got some suppression, exponential suppression in the size of the code, and then there's some constants here, which are basically like, this is something that depends on the lattice. But the important thing is, like, it's going like epsilon plus some corrections, which the corrections can be arbitrarily small. As long as tau is smaller than tau star, you can just increase L, and then you can make them arbitrarily close to 0.
Okay, gotcha. Another perhaps more naive question. So I can guess that your noise somehow depends on your lattice configuration, but does the recovery also depend on the lattice, or?
Yeah, that's a good question.
Because in the recovery, you only have a dependence on eta, but not on, I don't see L entering anywhere.
Yeah, so yeah, so you can also make the probability of, yeah, what can you do? So yeah, you have like this eta, which is like, that's just the noise, kind of the noise rate of your measurement errors, basically. And then what you can do is you can make it such that you have control over how, like, if this causes you to, how, given the noise on these measurement outcomes, this means you're gonna might make some mistakes when you try and correct the syndrome, correct the flux, right? And if you make mistakes there, then this can lead to mistakes when you do the error correction. But the thing is as you increase L for some value, for eta below some threshold, as you increase L, the probability of making a mistake becomes like very, very small. Is the important thing.
Oh, okay. Right.
So that means that, because you're, the probability of having like a big cluster of what can hurt you basically is, large connected clusters of errors. And this might make you make some mistakes, which mean that, you can get long error chains. That's the things that can hurt you. But as you increase the size, it's just like this standard like percolation theory stuff that, yeah, as you can increase the size, then for your eta below the threshold, it's just, you're very, very unlikely to have a big cluster that's going to hurt you. So every case is easy for it to deal with.
Gotcha. Thanks.
Okay, cool. So the last thing I'm talking about very quickly is talking about universal computation with this model. So, as we need a universal set of gates. So for example, we can take Hadamard T and C0. And our favorite type of logical gate is a transversal one because easy to do. It's a tensor product of unitaries, and it's also trivially fault tolerant because each qubit here is only, so any error on this qubit can only propagate forward to an error on that qubit. It can't spread. So that's what that's showing you. And then there's an important no-go theorem, which is proof for stabilizer codes, I think, by saying, and then more general codes by Easton and Canil. So for any quantum error correcting code, I think capable of correcting one erasure, then or something, or one error, I can't remember if it's error and erasure, but anyway, the set of transversal gates is not universal. And this seems bad, but then there's so many ways around this theorem. But one way to do it is to switch between codes with different transversal gates. And so the union of the transversal gates of both these codes is universal, but either one is not. For example, we can get Hadamard and C0 in the 3D subsystem toric code, and we can get T in the 3D stabilizer toric code. And the nice thing about code switching is that you can do this process by gauge fixing in constant time, and this is because of the single shot error correction, right? So if we can extract the syndrome reliably in constant time, then we can use that to set all the gauge qubits to a certain value. So this allows us the single shot error correction not only allows you to do error correction in constant time, but also gauge fixing. Because for example, you would just measure all the Z's gauge operators, and then you want to put them all in +1, which you can do. And the nice thing about this is that there's no time overhead for doing these. So you can do universal gate set with a constant time, and there's also no need for magic state distillation, which I mean, magic state distillation is a very nice method, and I think like sometimes people kind of act like it's a massive overhead, and I think like it depends on your parameters, but still I think it's the nice thing about this is the no time overhead as well. Okay, so how do you
time overhead? You mean constant time overhead?
Yeah, sorry. I mean,
it's a different relabeling of time. I mean, this is a
it's an order one time.
Talk to the experimentalists about order one.
Zero time.
Friends, but of course I understand.
Yeah. No, I just and like obviously like the constants are also important, and interestingly, like there was this paper by Alex, Michael Vasmer, and Christopher where they compared kind of sort of magic state distillation versus transversal gates in the gauge color code, and they found that magic state distillation was probably better. But I mean, I don't know what the outcome of such a comparison with this in this model would be. It was very interesting to think. Maybe it would. Who knows? But I think this has potential to. I think it's probably going to have potential to outperform the gauge color code just because. I actually asked Michael this at TGC, but the main overhead they have, the main reason that the transversal gates are not as good is because decoding the 3D color code is hard, and as we've seen, like the decoding performance of this code is better. So I think one of the main reasons that they found that the transversal gates weren't as good is actually not as much of a problem here. But that speculation is something that I think would be interesting to look at. Okay, so very quickly, you can make a 3D so as I said earlier, you need boundaries, but you can make some choice about the boundaries. So the code I presented earlier is like you take a cube and you have these boundaries, but you can also take like a tetrahedron. And this code is like kind of weird, but it's the way I always think about it is, so you're probably familiar with the tetrahedral 3D color code. You can take this thing and you can play a trick where you sort of do this unfolding on it, and then what you end up having is like 3 tetrahedral toric codes fused along the base, basically. And you can do this, and what you end up is like these 3 things that are fused along the base, like each one of them has a structure of the 3D subsystem toric code. So yeah, why is he put 3 qubits, 1 qubit? Okay. As is, the details of this are in Joseph Ivenson's thesis. But you have this. Okay. So what he's saying is on the base, at each of these locations on the base, there's 1 physical qubit, and then in the bulk up here, each of these locations has 3 physical qubits, and this is from like the 3 copies. So it's like people are probably familiar with this 2D folding thing. So you have a toric code defined on a square, then you can like fold it along its diagonal to get a triangle, and this is like a color code, and this is like the 3D generalization of this, but it's a lot more weird and awkward because you're sort of like trying to fold things in 3D through each other, which is but anyway, this is the structure you end up with. You have this base where you have 1 logical qubit, not logical, 1 physical qubit for each site, and then the bulk up here, 3 for each site. Yeah, and this is related to like how do you transform color codes into toric codes, and there's I'm working on a paper of like kind of explaining how this all works. But there's a nice interpretation of how to transform a color code into copies of toric codes by using kind of looking at small regions and running local unitaries which correspond to like the encoding circuits of small quantum codes. And here you can do C0 transversely because it's CSS. You can also CZ between boundaries, and you can also Hadamard. And these gates basically all, you can derive all of this from the 3D color code because this is it's basically equivalent to it. And then the nice thing is you can gauge fix to a 3D stabilizer toric code, as in the color code case, which has a transversal logical T gate. So this gives you the full set, and this is like one way you could think to do fault tolerant logic. And yeah, and then okay, here's some. It seems plausible that if you're limited in 2D, you could maybe use something like recent proposals by Bombin and Ben Brown, where you take like this just-in-time decoder and you slice your 3D object into these constant thickness 2D slices and you propagate through time, although it seems like doing this is going to be, there's going to be a price to pay in the threshold, definitely, I think.
So you're saying that this kind of bump-in trick, or that was done by Ben and further also developed, that would also work here. Are you saying that, or?
Yes. So like modulo, like we've not actually worked out the details, or at least I don't think they've worked out the details of this. But it seems that like the original paper Hector actually did was for the 3D tetrahedral color code. So I think it would actually be less work to translate it into this for this toric code I'm showing here than it was for Ben to translate it, because he changed it to these like ones on the cubic, not tetrahedral things. But it's not something that I think is being worked out in detail. But I don't see any reason why it wouldn't work in the same way. I think I can say that with that's as much as I can say.
Wonderful, thanks. That's great.
Okay, so yeah, sorry for overrunning here, but thanks for the questions. I'm very happy to talk about this stuff. So just to summarize, yeah, I've showed you this model of the 3D subsystem toric code. Trying to persuade you that it's simpler to understand than the gauge color code, for example, and I've explained how this single shot decoding works, where you can decode in the presence of measurement errors in constant time. And then I kind of gave you, I'm sorry I didn't like give you much details of how the proof works, but I tried to explain like the statement of the theorem and why we chose to write it like this, and because I think like, yeah, just understanding the right language and how to state these things in a nice way is like half the battle, I think. And then I also gave you a quick overview of one way of doing fault-tolerant universal gates in this model. Yeah, so thank you very much, and yeah, happy to take any questions.
Wonderful, that was spectacular, and we also already had lots of questions along the way. So are there more? Is there still a reservoir of questions left over? Now's your chance.
I guess sort of another naive question from my end. So when you're creating this 3D subsystem code, is there a unique way to create a subsystem code for any given quantum code, or are there multiple identifications that will allow you to obtain similar results?
Yeah, this is a good question, because I think it's not possible in general. Like the structure we had required quite a lot of symmetry, and because you need a way to define these local gauge generators in such a way that you have this property where you can build the stabilizers from different products. And for example, I did try and do this with the 3D, the regular 3D toric code, where so for that you take the simple cubic lattice with physical qubits on the edges, then your X operator is going to be a 6-body operator associated with the vertex, and the Z are going to be like these 4-body operators associated with the faces. So I wanted to like construct the subsystem version of that, because it's more familiar. It'd probably be easier it'd be probably better performance with the stabilizers at a lower weight, but I couldn't. I don't know how to do that. So I think in general, it's like the color code has this nice property where for any color code, there's like a kind of clear way of how to change it into a subsystem code. But I think that's the special thing of the color code, and for these toric codes, I don't think, at least I don't know how to do it. The way we like constructed this is by coming up with this specific example that I showed you. Then Alex like worked out a generalization, but it's not a generalization where you give me a 3D stabilizer toric code and I give you the subsystem version. It doesn't work like that. We can't do something that general.
And you just mentioned that you utilize certain symmetries. What precisely were the symmetries that you utilized in your construction?
Yeah, so the nice thing about okay, so this I'm still sharing the screen, right?
Yep.
Yeah, so this you see this this structure here. So actually, like, stabilizer versions of these codes would work as follows. So let's consider the so the Z guys are blue. Blue operators are Z. So this would be like a weight 3 Z operator, and then I would have like a weight 12 X operator here. So this would be like that's one toric code I can pick. I could also pick like I could say like, okay, actually I could say, okay, no, I'm going to have weight 3 X stabilizers and a weight 12 Z stabilizer. But you see that these like two choices are like, there's just a translation going on between them. So I have like this symmetry between X and Z here, which is like, which is the thing that's important. And this is like the property, actually it's a property of, in arbitrary dimensions above 3 or above, I can take like a cubic lattice and I can do this thing called alternation, which is like, so I have a cube, right? Then I can always select half of its vertices, and like I can select them. There's like there's two like obvious ways of doing this, such that the vertices don't share an edge. So I can take like the kind of opposite corners, if that makes sense. And then I can like join these up, these new vertices, if they share a face, and this is going to like create a tetrahedron. But there's 2 ways of doing this, and they have like they're rotationally symmetric, and I can do this in arbitrary dimensions above 3 or above, and this will give me like something with this nice symmetry where like the X and the Z are sort of like just a translation or rotation away from each other, and this structure will allow me to define this subsystem toric code nicely.
Wonderful. In the when you discuss like these like more rigorous approaches and look at these ideal minimum weight perfect matching decoding channels, I mean, how specific is that? How much is that glued to this specific decoder, or does that framework also hold more generally?
Yeah, yeah, it's an interesting question. I mean, so yeah, I think like often people look at these minimum weight matching channels as like a nice theoretical thing to look at as well. And the nice thing here is that actually, like, you know, people sometimes assume this, but it's like you can't actually do that efficiently, but we can actually do it efficiently. But the other thing to relax maybe is to say, okay, can I like actually have like instead of finding the minimum weight operator, the minimum weight correction, can I find something of comparable weight to the minimum weight corrections? Like, can I approximately solve the problem with some approximation ratio? And there, I think it's like, I think we tried to prove something like this, but we didn't actually manage to do it. Because, you know, if you're considering like a more complex, so for example, another thing I've been looking at a bit with Jacob Bridgman and Alex is looking at what happens if you take this model and have QDITs. And there, like the error correction problem, you can say I want to find the minimum weight solution, but doing that efficiently is not. There's no algorithm, because it's like matching on a hypergraph. So it's NP. I don't know if it's NP hard, but there's no P polytime algorithm to do that.
Yes,
so we wanted to, but maybe you can approximate it, but then it's like hard to make the proof carry through.
Oh yeah, of course, I understand. No, of course, that's tricky, but that's kind of somebody else's problem that you're going to inherit here. Yeah, I understand. Okay, good. Thanks. Are there more questions?
Yeah, I have another question on, you mentioned at some point that you expect circuit level noise to be not so severe because you're preventing hook errors just by your stabilizer scheduling, right? So I mean, if I understand correctly, the reason why hook errors are so harmful is often because you use minimum weight perfect matching. Right? So I mean, if instead you just like write up some lookup table, which errors propagate where, then and you manage to like assign every syndrome uniquely to some origin error, then you would never need to worry about hook errors anyways. So I was wondering, like, these single shot techniques, how much do they rely on? I mean, they seem to rely quite heavily on you using minimum weight perfect matching, right? How adaptable is this single shot property to other decoders? Yeah,
that's it. Yeah, I mean, that's a good point about like, so the assumption when I said it's better for circuit, like, yeah, so I was imagining using minimum weight matching again for the circuit noise case, which is why we were worried about the hook errors. But yeah, the question of like, could we use other decoders? At least for like the second step of like, you know, of doing the error correction in the kind of once it's basically like a stabilizer code problem, you could use something like union find if you wanted to make it faster. And I think you could probably use that for the first step as well, although I'd have to think a bit more about that. But yeah, it's an interesting question about like, because we proved this theorem for a very specific decoder. I think it will hold more generally, but like, I mean, yeah, because in practice, like you don't actually want to use mirror weight matching in the real world because it's way too slow.
Right.
So yeah, the question of what other decoders would work for this problem is an interesting one, and I think especially like looking for efficient ones.
Yeah.
But it's not something that like we've investigated theoretically and also haven't really done numerically yet either.
Okay. I mean, maybe another question that's not so concrete to this example, but so say you have say you don't look for an efficient decoder, you just take whatever optimal decoder you have with every knowledge about the circuits and about how every error propagates in these circuits. Do you think you can? Do you think single shot quantum error correction is still possible with on circuit level noise? Just using. Okay, maybe this is a dumb question.
I think so. Yeah, I mean, but like if you're doing that, then you're limited to. I'm not sure you could ever actually. The smallest example of this probably still has like quite a lot of qubits.
I think because if all stabilizers you're measuring are weight 3, then the thing is with hook error, right? It will be stabilizer equivalent to some weight 1 error, or hook error will just be a stabilizer. But,
no, I mean yeah, okay, that's when you measure weight 3 stabilizer. But I mean, say you have like a toric code or something with some other homological code, then you're going to have other hook errors.
yeah, okay.
Oh, so you're saying like in general, if you had the toric code and you could use single shot because yeah,
just any code, like how far towards single shot can you get with like unlimited decoding power and knowledge of the system?
Yeah, I think you can. I think you're still going to be in trouble if you measure like the local generators of the toric code, even if you have like optimal decoding.
Well, because you don't have the correct input to the decoder with your measurement errors, right? So
yeah, exactly. So you're just, no matter what you do, you have because you can get stuff like arbitrary far away just quite easily, so then it can make a mistake pretty easily. But like if you have the toric code and you allow yourself to measure, as I said earlier, like non-local generators, then you can build a set of generators which is single shot. It's just that you lose, it seems you inevitably lose the geometric locality. So what we wanted to do is retain that and still have a generating set that's single shot.
Okay. Yeah, I mean, what I was thinking about was that, like, if you look at circuit level noise, then like the errors that create pure measurement errors, that is like say bit flips that happen right before the measurement on the ancilla only. So errors that do not spread, only flips the measurement outcome. These are quite rare compared to everything else, right? Like every other error, like the typical error would like spread around, and also trigger some other ancillas and so on and so on. So, but no, I would expect on average to be able to like see more pattern.
Yeah. I don't know.
Maybe this
no, it's interesting. Like we've only just started looking at the circuits for extracting the syndrome and stuff. But that's a very good point about like what is the typical error from one of these circuits compared to.
Once you fix the circuit, you still have like a finite probability of getting one of these errors that doesn't spread out at all, and then you're always.
Yeah.
Yes.
So you're not going to get a threshold. Unless you also make your circuit.
Well, I mean, do you have a...
And then it's
okay. Right. Okay. Yeah, I think about that. Thanks.
I have another question, if I may. So on this picture that's now on the bottom right, on the top right of the screen, so there you do the first decoding step where you just match these gray balls.
Yeah.
And because you, oh no, you actually have the same problem, but you don't really care about the color of this string, right? If it's a green or a yellow string for the match.
Yeah, you just match color agnostic at this point. The color is only used in like to estimate to give the stabilizer syndrome afterwards. So in this step, you just like.
If you go about it a bit cleverly, for example, the loop on the bottom right of this subfigure, like if you match it with a green one, then you like don't have to do anything in the second step. Or also the bottom there we have this like bicolored open loop. There it depends a bit on where you put your like the second change of color for your decoding. So that might.
Yeah, this is a good point. Like, this is an optimization we haven't looked at, but like, yeah, as you say, like if you've got a yellow loop and you close it with yellow, then there's no correction to do. So, like, what maybe there would be, you could be smart about what color path you chose. Also, because if you chose a path that's like going yellow, green a lot, then that's going to be like having lots of stuff to do next time. So maybe you don't want to do that. That's a very interesting like question, but it's not something we just did. Like the simplest matching thing we could do.
But that's just the shortest path always.
And yeah, always the shortest. But like I think you could add like some penalty for like because you could have some function of like have the cost of your path, and like there could be a penalty for like having lots of different colored edges in it, for example. I think that'd be probably something you could do. But it's not something we've explored. But yeah, I think maybe for optimizing the performance, it might be interesting to look at that.
I have another question related to an earlier point that you made regarding self-correction. So I guess with that Sam Roberts paper, it was like they took like a 3D lattice and they decorated like part of its 2D edge with some sort of symmetry, and that's how they got their self-correction. So with regards to your model, is there some additional symmetry that you could add on one of the boundaries in order to argue that you're in basically a self-correction phase?
Yeah, that's a really interesting question. So I'm not like super familiar with how that works, but it's definitely something that we think would be worth looking at. And like this thing seems to have a lot of similarities with the color code, which is one of the models they achieve that with, I think. So I wouldn't be surprised if it would work in a similar way.
Wonderful. Good. There was quite a discussion. Wonderful. That's great. And thanks for all these insights. That was really very good to go through all these details. Very nice. And thanks to all for the many questions and the interest. Yeah, I mean, there could be much more to be discussed, but maybe we kind of keep it a bit at bay. Otherwise, might lose people. So thanks so much again for this wonderful, exciting talk. It was extremely insightful, and there was a lot more coming out of this than we knew. So thank you all for listening. Thank you for giving this wonderful talk, and see you around in another constellation very soon, I hope.
Yeah, thank you. And thanks. This is the best audience questions and discussion I've had on an online talk ever. So it's really
okay. That's wonderful. That's quite a compliment. Okay, thank you. Have a
Thanks.
Say hi to Alex.
Yeah.
Thank you.
Yeah, exactly. Say hi.